Welcome back. In the last part of this section, we're going to introduce a few more definitions. Remember that I said that an event is basically just a set. And we know from chapter 3 that sets could be as little as having 0 things inside them, if they're the empty set, or they could be as big as having everything inside of them, if we're thinking about the universe. The same thing is true for events. We could have an event that's as small as having nothing inside of it, or we could have an event that's as big as having everything, all the possible outcomes inside of it. If you have an event that has nothing inside of it, you would call that an empty event, just like you would call it the empty set. But the other name that we might give to this would be calling it an impossible event. And the reason we're saying it's impossible is because remember that when we observe an event occurring, we've observed one of its outcomes. And if you are an event and don't have any outcomes inside, then you could never occur because there's nothing to observe. So if you have a special event that's an empty set kind of an event, that's something that's guaranteed will never be observed, so is guaranteed to never occur. It is an impossible event, and we know impossible things have a probability of 0. The other extreme, when we have an event that contains all the possible outcomes, we call that a guaranteed event. And the reason we say guaranteed is because since it has all the possible outcomes for the experiment inside of it, then no matter what happens, you will observe one of its outcomes. So no matter what will happen, you will see one of the things from the sample space happening. So if your event is the sample space, if it has all the possible outcomes, you're guaranteed you will see that thing happen. So we know then that if you have an empty event, the empty set, its probability should be 0. And if you have an event that's essentially the entire sample space, then you're guaranteed it has a probability of 1 because it must occur. So let's do an example now. And part of this is motivated by explaining why do we care about these two things. So how would these things occur? Well, let's think about this experiment where I'm rolling a 6-sided die. And so I know for this experiment there should be 6 outcomes. I could see a 1 or a 2 or a 3 or a 4 or a 5 or a 6. And now let's think about these two events that I've defined. I've defined the event E as being the event where I roll a number which is not even and also not odd. So if I'm thinking about all of the numbers that I might observe, every single one of them is either even or it's odd. There is no number that's not even and also not odd. So 1 wouldn't be inside because it's odd. 2 is not inside of E because it's even. All of these numbers, they're either even or they're odd, so none of them are included inside of E. E doesn't have anything inside of it. E is the empty set. So I can say the probability of E happening is the probability of the empty event happening, which should be 0. The chance that you will roll a number that's not an even number and also not an odd number is 0 because there aren't any numbers that are not even and not odd on your 6-sided die. The other event that we're looking at, F, that's the event that we roll a number that is even or odd. And if I think about listing all the things inside of F, that would be all the numbers that are even or odd. And I've got, here's all the even ones, 2, 4, and 6. And here's all the odd ones, 1, 3, and 5. And then I notice, wait, I've listed everything that's inside the sample space. So when I'm talking about F, really I'm talking about the sample space. So I know that I'm guaranteed no matter what happens, you will see a number that's even or odd. You'll see something happen. So you are guaranteed that F will occur. Probability of F happening is 1. Okay, another little thing to introduce is the idea of disjoint or mutually exclusive events. We did talk about disjoint sets before, and it's the same idea here. If we're disjoint, then we don't overlap. There's nothing in common. So when we're talking about disjoint or mutually exclusive events, those are events where the intersection is the empty set. So in other words, there are no outcomes where E is happening and also F is happening at the same time. In other words, it's impossible for the two things to happen simultaneously. So if you knew that E intersect F was the empty set, And if I told you E was happening, then you know F certainly would not be happening. Or if you knew that F was happening, then you would know that there's no way that E could be happening. And there's lots of ways that you could have disjoint or mutually exclusive events happening in occurring in an experiment. So here I've got my card selecting experiment. Select a card from a deck of playing cards. E is card is red, F is the event, card is a club. And if I think about the things that are inside of E, those would be all of my hearts and all of my diamonds. F, that's all of the clubs. There's no card that's going to be inside of both of those events. There's no card that's red and also a club at the same time. So E intersect F has nothing inside of it. E intersect F is the empty set, which also tells you that the probability of E intersect F, the probability that we will get a card that is a red club, should be 0. Because, of course, it's an impossible event. If you have two things that are disjoint, then the two things happening at the same time is guaranteed, will never occur. So let's do an example. I've got myself a 6-sided die that I'm rolling, and I've got 4 events. A is that we're rolling an even number. B, we're rolling a 5 or a 6. C, we're rolling a 5 or a 1. D, we're rolling a 3. Maybe I should just list all these things. I think that might be nice. A, we're rolling an even number, so a 2, 4, or a 6. B, we're rolling a 5 or a 6. C, we're rolling a 5 or a 1. And D, we're rolling a 3. And we're interested in who's disjoint, who's not disjoint. So A and B, are they disjoint? No, they are not. And that's because A intersect B has something inside of it. There's a 6 that's inside of A intersect B. A and C, are they disjoint? A has a 2, 4, and a 6, and C has a 5 and a 1. I will say yes to that, and that's because A intersect C is the empty event, nothing inside of it. A and D, 2, 4, 6, 3. Yep, there's nothing in common between A and D, so that's another empty event. B and C both contain a 5. So B intersect C is not empty. So sorry, they are not disjoint. B and D, 5 and 6. D has a 3 in it. They are definitely non-overlapping. B intersect D is the empty event. So yes, mutually exclusive. And then finally, C and D. C has a 5 and a 1, and D has a 3. And yep, there's nothing in common with those. So C intersect D also is the empty set.